In this segment, we're going to take a look at the relationship between hybridization and molecular shape. The basis for this discussion really goes back to the valence shell electron pair repulsion theory, or the VSEPR theory from your general chemistry class, which recall that VSEPR theory states that electron pairs tend to repel each other as much as possible. And so electrons, meaning the covalent bonds and the lone pairs, are going to try to migrate as far away as possible around a central atom to separate themselves by the largest possible angles that they can be separated by. So if we think about an atom that's four different regions of electron density or four different separate bonds, single bonds coming from it, for example, the largest possible separation for that would be a tetrahedral shape with a 109.5-degree bond angle. So what we're going to do is look at, in the form of a table, the relationship between hybridization state, that being the sp, sp2, and sp3 hybrid orbitals, regions of electron density, and the predicted distribution of electrons, or the shape of the molecule relative to that atom, because the molecular shape is going to be one of the factors that determines how molecules behave and what types of structures and what types of impacts those structures can have on things like the biological function of a molecule, whether it could be active as a drug or things like that. So we need to start thinking about the shapes of molecules. So as we look at that, what we're going to do is we're going to fill in this table to look at the relationship between hybridization and the molecular shape. So we're going to fill in a column of this called hybridization, where the hybridization is what we're referring to as sp, sp2, sp3 hybridization state. So we're going to start by looking at the different numbers of regions of electron density that we can be up against. And when we're thinking about molecules that fill the octet rule, which is most of the things that we're dealing with in terms of our organic chemistry class, our number of regions of electron density is going to max out generally at 4. So when we talk about regions of electron density, what we're referring to is the number of atoms that are bonded to the atom that we're focusing on, and the number of lone pairs that the atom we're focusing on. So when we're talking about regions of electron density, we're focusing on one individual atom within a molecule, and we're looking at how many additional atoms that one we're focusing on is bonded to, and how many lone pair electrons it has, where each atom that it's bonded to is going to represent one region of electron density, and each lone pair is going to represent a region of electron density. So number of regions of electron density, our options here are going to be, we could have a molecule that has 4 regions of electron density, 3 regions of electron density, or 2 regions of electron density. So if we have 4 regions of electron density, and those electron density regions are spaced as far apart as possible, space those as far apart as possible, that's going to result in a 109.5-degree ideal bond angle. And if we have 109.5 degrees separating all of the individual bonds, the shape of the molecule relative to that atom that we're focusing on is going to be a tetrahedral shape. And for the tetrahedral shape, one way that we can draw that to show it accurately is we can show lines to represent bonds that are within the plane of the page. So those lines I'm showing in red. We can draw a wedge, which represents a bond coming out of the page. So that would be a bond that is facing you, and I'm showing that in blue. And we can use a dash to show a bond that points away from us. So this would be our typical tetrahedral shape. This is the shape that we'll be dealing with if we have a carbon atom that's bonded to 4 additional atoms. And so when we look at this and we're thinking about the bond angles that are present here, each of these bonds that I'm going to show in yellow, each of those bonds is going to be 109.5 degrees as our ideal tetrahedral shape there. So that's going to be our tetrahedral, and we could build a molecular model of this by taking out of your molecular model kit one of the carbon atoms, which are black, and forming 4 bonds to that to whatever other atoms that you wanted to. And you would see that the shape of that would be representative of a tetrahedron. Anytime we have 4 regions of electron density, the type of hybridization, or the representation of S character versus P character of the molecular orbitals, is going to be an sp3 hybridization. So when we say sp3, the way that we can think of this and relate that to regions of electron density is you can really think of it as being s to the 1 power and p to the 3, p to the 3rd power. So s to the 1 and p to the 3rd. And to help in relating that to number of regions of electron density, if you take all those superscripts and add them together, you get a total of 4, which matches up with the number of regions of electron density. Now that's going to be true all the way down the board here. When we think about the different hybridization states of sp, sp2, and sp3, and how they relate back to the number of regions of electron density. So anytime you have 4 regions of electron density, we're going to expect sp3 hybridization, where we can think of that as s to the 1, p to the 3, hence the total sum there is 4, and there's 4 regions of electron density. So going down the page and following this trend of hybridization, if we have 3 regions of electron density, you can think about what you would expect the hybridization to be. We expect that 3 regions of electron density means that the hybridization states need to add up to 3. So you do sp, and you can at most always have just one s orbital, and then we need to fill in the number of p's required. So s to the 1, p to the 2, 2 plus 1 gives 3, 3 regions of electron density. And if we want to spread those 3 regions of electron density as far apart from one another as possible, the way to do that is going to be to make a trigonal planar shape. So we're separating 3 regions of electron density here. So it'd be something like this that I've drawn there, and that atom in the middle in blue is the one that is our focal point here. That's the one that has 3 regions of electron density around it. Each of those 3 bonds, which I'm showing in yellow here, would have a bond angle of 120 degrees. So these are spread out into a planar shape like the propeller of an airplane, where there's a 120 degree bond angle separating each of those 3. That 120 degree trigonal planar bond angle means that the 3 atoms are all going to be in the same plane. They're laying flat relative to one another. And that will have important implications later on in the semester when we think about the types of chemical reactions that molecules undergo and how they're going to interact with one another physically in physical space in those chemical reactions. So that's going to be referred to as our trigonal planar shape. So I'll go ahead and write that in here in this little bit of remaining space. And then going on down the list here, if we have 2 regions of electron density and thinking about the hybridization state and filling in s, always has to be s to the 1. P is what we fill in with a variable there so that our sum of the s and p equals the number of regions of electron density. So we need s to the 1 and p to the 1 to give 1 plus 1 makes 2 regions of electron density. So we're good to go there. Our bond angle, if we're thinking about having just 2 regions of electron density, that would be a scenario where, for example, we had a carbon atom or whatever other atom you want, and it has just 2 regions of electron density around it. If we have 2 regions of electron density and that is all, so we could draw 2 regions of electron density in there, and we want to separate those regions as far apart as possible, that's going to result in our bond angles here needing to be 180 degrees or a straight line. So we'll go ahead and fill in that that would represent a linear molecule. What we're going to do now with these, now that we have some kind of vague general information filled in, is we're going to fill in with a couple of specific examples of molecules that fit these criteria. So if we're thinking about an sp3 atom, and we're focusing here predominantly on the chemistry of carbon atoms, we're going to use carbons as our example, we could do something like ethane. C2H6 is the molecular formula of this, and we think about the 2 carbon atoms here. Both of these 2 carbons we would expect to be sp3 carbons. So both the carbon here on the right and the carbon on the left, both sp3, because if we count the regions of electron density around each of those 2 carbon atoms, we would see that both of them have 4 regions of electron density, so therefore sp3. And the predicted bond angle around each of those carbons would be that 109.5 degree bond angle. If we come on down to the next line, and we think about a carbon atom that has 3 regions of electron density, one way to do that is to do ethene, an alkene, a molecule with a carbon-carbon double bond. So you can go ahead and fill this in. This would be our Lewis structure for this. And in both of those carbon atoms, so carbon atom here and the carbon atom here, then I'm putting both in blue, we'd expect those to be sp2 carbon atoms because each of those 2 carbons, each one has 3 regions of electron density. So this carbon has 3 regions of electron density shown in blue, 1 region to the hydrogen here, 1 region to the hydrogen here, and then a 3rd region reaching over to that other carbon atom. Just because there's a double bond there, it's still just 1 region of electron density. So that's going to mean 3 regions of electron density in total, hence an sp2 carbon at both of those locations, and hence the bond angle would be 120 degrees or trigonal planar, meaning that molecule is going to lay flat. So relative to those 2 carbons, we'd expect the structure to be laying flat. You could build a molecular model of this pretty easily if you have your molecular model kit. So our sp carbon is going to be a carbon that has just 2 regions of electron density. And that's going to imply that the carbon has a triple bond to something else. A carbon-carbon triple bond is one example to make a so-called alkyne molecule. We can fill in some hydrogens or whatever other atoms we want here. And looking at this structure and thinking about the hybridization state of it, this carbon on the left, as well as the carbon on the right, each of those 2 carbons have just 2 regions of electron density apiece. So therefore they are sp, and they'd have a 180-degree bond angle. And I've tried to show that accurately in the drawing here, since it is a planar linear structure. I've gone ahead and drawn it linear as well. Just as in the sp2 example, I tried to draw those bonds approximately 120-degree bond angles, trigonal planar here, here, and here, and here, here, and here in yellow. For the sp3, I didn't even attempt that. I could have tried to draw 2 tetrahedral carbons side by side, but I did not bother with that. But certainly you could do a tetrahedral shape there if you wanted, with the 2 lines, a wedge, and a dash to indicate that 3-dimensional shape. So these are going to be the 3 general shapes or forms that we'll look at relative to carbon atoms that are going to have an impact on some of the outcomes of chemical reactions that these will undergo, and they'll also often have a very dramatic impact on the interaction between these molecules and these atoms and their biological targets. For example, in drug design, one of the primary things that happens is that we design molecules to have 3-dimensional shapes that will bind very tightly to the 3-dimensional shape of a protein target, so that that protein target can be inhibited or activated, whatever needs to be done in order to cure the disease we're trying to cure. And the molecular shape of the small molecule, the organic molecule that's coming in and binding or docking to the protein, needs to be spot on. And so for that binding to be spot on, we need the molecular shape of each individual atom to be tailored to be nice and complementary to the protein that we're trying to target in our drug design experiments. So it's really important to get familiar with the shapes relative to each individual atom. And we're also going to be looking at some additional details about molecular shape as we get onward in the semester as well. So with that, there's another thing that we need to mention with regard to molecular shape and this concept of double bonds, single bonds, and triple bonds. And that is when we think about carbon-carbon single bonds relative to double bonds and triple bonds, in addition to having differences in the shape, they also have differences in the rotation, meaning whether we're able to rotate around those carbon-carbon bonds or not to allow the molecule to spin about those different bonds. So we're going to look at rotation about bonds. And when we talk about single bonds, particularly single bonds in an acyclic molecule, acyclic meaning without a ring, where the atoms are not part of a ring. The ring can sometimes lock the atoms into place so that the atoms will behave in ways that they don't normally behave. But we have single bonds in acyclic systems. We expect for there to be relatively free rotation around carbon-carbon single bonds, or even other single bonds. So in other words, what atom is pointed forward versus backwards within the molecule at any given moment can change because we're rotating around the carbon-carbon single bonds. And if you have a molecular model kit, I definitely encourage you to construct a molecule where the atoms are connected by single bonds and see for yourself how you can rotate around those bonds to illustrate the different so-called conformations, different ways of rotating around the carbon-carbon bonds. So single bonds in acyclic systems are able to rotate relatively freely for our intents and purposes, at least at the moment. Double bonds and triple bonds, in other words, pi bond systems, instead are going to be relatively locked into place. It requires an awful lot of energy to rotate around those bonds. And so those bonds are not going to rotate freely. Instead, we're generally going to consider those bonds to be locked into place. So those bonds do not rotate freely. And you can also illustrate this for yourself if you have a molecular model kit as well, by building a molecule that is an alkene, such as that 2-carbon molecule that we drew up above here, where the 2 carbon atoms were connected with a double bond, and see for yourself how once you put in a double bond, that makes the molecule really rigid. And due to that rigidity and the inability to rotate around that carbon-carbon double bond, that's going to impact the types of ways that that molecule will be able to interact with others, because it's not going to be able to rotate and flip around. Instead, it's going to be relatively locked into place. So when we think about double bonds, triple bonds, when you look at those structures, think of those atoms relative to the carbon-carbon double bond as being locked into place. Whereas if you look at atoms around the single bond, be thinking that you can rotate around the molecule, flip it over and whatnot to change some of the locations of those atoms. Even if you're changing the locations, though, the bond angles are still going to stay the same within the molecule. And you can demonstrate that with your molecular model as well. As you rotate around bonds, you're just moving the atoms around in the molecule, rotating them around in the molecule, and you're not changing the bond angles during that process. Pi bonds, on the other hand, double bonds and triple bonds are not going to rotate very freely at all. And so we're generally going to consider those to be fixed into place, or those to be rigidly locked into place atoms. So with that, we conclude, and we will go on to our next topic next time.